Okay, welcome to the Science Seminar. I have the privilege of introducing our guest speaker today, and I'll just make it very brief, but I have to say this because Abbey, who her last name was Jeske, and she's got her family today. Her dad's here, her husband Alex is here, and little Bear is here as well, their little baby. She was Jeske back then. Her name is Rickards today. This must have been about 10 years ago. She came with her mom to visit, and she was wanting to study astrophysics at some university that had a strong astrophysics program. And her mom was saying to her, just visit LeTourneau. That's all you have to do. You don't have to go there. Just visit LeTourneau and just see what it's like. And so I got to visit with Abbey back there about 10 years ago, and I could tell this was a very sharp young lady, and right away. And so she wanted me to describe the physics program here at LeTourneau, and so I did to her. And but you know, I wondered in the back of my mind, am I going to challenge this young lady enough in this physics program here to convince her to come? And praise the Lord, she decided to come to LeTourneau, and I hope she has no regrets about that. She got her bachelor's degree in engineering physics back in 2013, and she was one of 3 students that graduated in the science programs that May that had perfect 4.0 averages and were just top-notch students. And I was expecting all these top-notch students to go directly off to grad school. But that didn't happen right away. Abbey decided to, teach at a high school, Brook Hill High School in Bullard for 4 years. She got married to her husband, Alex, and Alex works out at Eastman now. And so she made a life around here, but, you know, I saw her again. She came back a couple of years ago and said, Dr. Ball, I'm really getting the itch to do some more. Something more in physics. I'd like to do some graduate work. And so we explored the possibilities of her doing graduate work. And she connected with the same university that her dad got his master's at, Stephen F. Austin. And so and her dad does some interesting work in geology, and he does work testing about whether dump sites are leaking anything with some very sophisticated techniques. And so we've had him speak here in the science seminar before. But Abbey went there and started work on her master's degree in physics. And what, a year and a half later here, she's graduating. She just defended her thesis on Monday and passed. And so congratulations, Abbey. And so,
thank you guys for having me back. I'm excited to be here, and I'm excited to have a do-over, if you will, of my thesis defense, where I'm not quite so nervous. I'm going to try to keep it a little simpler than I did for my professors. They're all super familiar with this and know way more than I do, but I'm assuming most of you guys haven't done much astronomy, so we're going to try to explain terms as we go. So my thesis was a photometric study of the eclipsing binary V574 Lyra. And I had someone tell me last night that sounds like I'm reciting the digits of pi. So let's kind of dig in. Does this work? We'll just use this. All right, so a general outline of what we'll go over today, just an introduction, justification behind my thesis, the objectives I had, and then the interesting stuff, my methods and apparatus, so the equipment that I actually used and the techniques I actually used to study this star, how I took my observations of the star, something called a period study. An eclipsing binary actually has 2 stars that rotate around each other, and so they have a certain orbital period, but it's only been measured a few times. And so by doing a period study, you can actually find the orbital period more precisely. And then a Wilson-Diviney solution, which is a computer model, or computer simulation of these 2 stars. And then a binary maker 3 model, which is just a 3D representation of what the stars could look like. So this picture right here is actually the constellation Lyra. And my star, if you take these 2 stars here, draw a line upward, those two stars over there draw a line upward, and you'll see that they intersect around the top of the slide, and then go about halfway back down, and my star is on the very edge of the picture, which you can't actually see it. It's a very dim star, so it's not visible to the naked eye. All right. So I mentioned that I did a photometric study, so it would be helpful to know what photometry is. Simply put, it's just a measurement of brightness within a certain range of wavelengths. So this is actually one of the measurements that I took of my star. And you can see over here on the vertical axis, we've got something called magnitude. That's just a scale used to measure the brightness of stars, and it's actually an inverse scale. So the smaller the number, the brighter the star is. So you can see at its brightest, my star is about magnitude 12.9, at its dimmest around 13.6. And those are way, way dimmer than you can actually see with your naked eye. You can also see that my star is not constant in magnitude. It's what's called a variable star. And you can think about this change in brightness making sense if you think about the two stars orbiting each other. So let's say you've got two stars and they're facing you broadside. And that's going to be the most light you can possibly see from those two stars. So those are going to be places where the stars are facing you are going to be the places where you have the most light. Those are our maxima. And if one star is blocking the other, then those are going to be our minima. You can see that my minima are two different depths. That means one star is significantly brighter than the other. So this is where the brighter star is being blocked. That's called a primary minima. This is where the less bright star is being blocked, and that's called a secondary minima. Okay, so we're dealing with binary star systems, and there's actually a lot of different types of binary star systems. So the shape I just showed you and the shapes that you see here, these are called light curves. And it used to be that we would sort binary star systems based on the shape of their light curve. And it turned out that was not a very good system. So our old categories were Algol, Beta Lyra, and W Ursa Majoris, which we shortened to W Yuma. And the reason that those weren't good categories is you often had stars that would exhibit characteristics of, say, 2 of the categories, or none of the categories. And so you couldn't classify a lot of these stars. So there was a new classification system developed based on the physical configurations of the stars. So what they actually look like, what their shapes are. So the 3 categories for this new system are detached, where you have 2 stars orbiting each other, but they're not touching each other at all. There's no mass transfer between them. There's semi-detached, where one star has grown so large that it starts feeding mass to the other star. And then there's contact, where both stars have grown so large that they're starting to merge. So why should we even bother studying binary stars? Well, our galaxy alone is over 50% binary stars. So that's a pretty significant reason in and of itself. But another reason is we need more data to understand how stars gravitationally and magnetically interact with each other. And since binary stars, especially close binary stars, are gravitationally interacting, and contact binary stars are magnetically interacting, then we can study those stars, determine their physical parameters, and come up with better ideas about how stars gravitationally and magnetically interact. This picture here is actually of our Milky Way galaxy. It's from NASA, but it's in the X-ray range of wavelengths. Okay, so my personal objectives. I wanted to observe an unmodeled binary star using CCD photometry. CCD photometry is just a method of taking pictures. So a CCD chip is a charge-coupled device. It's widely used in astronomy to take high-resolution pictures of stars. And by unmodeled, I meant that nobody had done a mathematical model on it before. I wanted to be the first. So then I also wanted to complete the period study to make sure that I knew exactly what the orbital period was of my 2 stars. then determine the possible physical parameters, so I wanted to be the one to model it, and then create the synthetic light curves. So you saw some observed light curves earlier. I wanted to create ones from the mathematical model, and then create a 3D representation of the system. So actually see what it could look like. Okay, so then I had to pick a star. And there's lots of stars in the sky. Now, for my telescope that I was using, I needed a star that was brighter than magnitude 14. So 14 or less. Remember, smaller numbers a brighter star. And I wanted it to be visible from June to October. The reason for that was June, I was starting my research. I wanted to do it over the summer. October, well, I was due with him in November, so I figured October was probably a pretty good stopping spot. So in the night, there are actually 3 different types of twilight. There's civil twilight, nautical twilight, and astronomical twilight. And astronomical twilight is the darkest part of the night. And so I wanted to know when astronomical twilight was in June. And it turns out it was from about 10 p.m. to 4:30 a.m. And in October, and it turns out it was from about 8:30 p.m. to 6 o'clock a.m. And I wanted to take as few measurements as possible on this star so I could get done with my research quickly. And to do that, you would like to be able to see an entire cycle of these 2 binary stars over the course of one night. And so I knew that my orbital period needed to be no longer than 6.5 hours, because that's all the time I had in June. So then I looked at available data, and there's actually an entire catalog of variable stars called the Variable Star Index. And they allow you to search variable stars based on their location, what constellation they're in. So I wanted to get a general idea of what constellations were up in June and October. So I pulled up Sky and Telescope's interactive star chart, and I looked in June, and I looked at what was rising in the east, and I looked a little further north, because constellations in the north are visible longer. In fact, if you look around Polaris, they're visible all year round. And so that area I circled on that star chart were the constellations I started considering. And just to make sure, I also checked in October and saw if the same constellations were going to be visible 6.5 hours after the start of astronomical twilight. So I looked, and yes, there were a couple overlaps. So here we've got Cygnus, Lyra, Draco, Ursa Minor, Cepheus. And in October, you can see we have Cygnus, Lyra, Draco, Ursa Minor, Cepheus. So those are the ones I started looking at and searching. And there were lists of hundreds and hundreds of stars. So fortunately for me, there are these surveys called all-sky surveys, and they actually use satellites and other observing stations to look at these stars and just compile tons of data and spit out rough light curves. And so I was able to look at the rough light curves and see whether or not a particular star was an eclipsing binary. So I came up with a list of almost 20 stars. Tried to go through, make sure that nobody had published a model of the star, and that the eclipses of the star were total or near total. Now the reason I wanted to do that is if the eclipse is total or near total, you can actually pin down the mass ratio between the 2 stars, and it's a lot easier to find that mathematical model. Otherwise, you got to do, well, I'll tell you about that in a minute. So my target ended up being, as you could probably guess, B574 Lyra. All right, so the interesting stuff, apparatus, what I used. So SFA actually has an observatory. It's off campus, it's north of Nacogdoches, and it's got some impressive telescopes. But the issue with them is between projects, they get messed with, which is not a bad thing. It's just, it takes some time to get them back calibrated, and I didn't exactly have that time. So fortunately, one of the professors also has a private observatory, and his observatory is called Waffalo Creek Observatory. And he has just this one telescope, but man, is it a good telescope. It's a .36 Ritchie-Cretan telescope. And you can see it, the telescope itself is just right here, that's it. And it has a robotic German equatorial mount, which is over here. And it's got a CCD camera, which again is just that high-res camera that I was telling you about. These cameras are also used for astrophotography. So if you're just a photographer and you want to take really good pictures of stars and galaxies and nebula, this is what you would use. But it's also good for photometry. And then I used a set of filters. So I mentioned that photometry, you have to look at a certain range of wavelengths. These particular filters are called the Sloan filters. And I used only 3 of them, the ones that corresponded to visible light. So the G filter here in blue, the R filter in green, and the I filter that's labeled I, and then it's red. And then that corresponds to almost the entire visible spectrum, plus a little bit of infrared. And then there was a focuser, which I didn't have a picture of because it's behind the camera, between the camera and the telescope. And a flat panel light source, which I'll explain the use of in a minute. Okay, the really cool thing about this guy's observatory, his name is Mr. Michaels, is that every single thing that I just mentioned is connected via USB to an observing station inside his house. So he doesn't even have to go outside except to take the dust cover off the telescope. So to do the observations, here I am sitting at the desk. And I just go on the computer and I turn on the power strip and I turn on the telescope and the fans and the camera. And then I turn on the cooler for the camera. The camera, you actually want to cool the chip. It's got some thermal fluctuations in it, so you want to cool it to -30 degrees Celsius. And then you take calibration frames. You want to get rid of as much error as possible, error from the camera itself, error from dust in the telescope, and error from the background of the night sky as well. We have some software that helps with that. And then I just run a startup script. And the startup script turns on the telescope, moves it out of its park position. Actually, before that, it opens the roof so that the telescope doesn't run into the roof. And then I can write a new script that tells it my target coordinates and how long I want the shutter open and what filter I want to use and what time I want to start observations and what time I want to end observations. And I just click start and I run it, and the program takes pictures for me all night long. I don't even have to be there. I think the latest I had to be there was 10:30 at night. So you watch the first few frames, and then you make sure that they're doing exactly what you want them to do, and that's it. And you don't even have to worry about the weather. There are 2 weather stations, little bitty sets of sensors that Mr. Michaels has at his observatory. And anytime they detect cloud cover above a certain amount, then they automatically park the telescope and shut everything down, save the data, and I just go in and pick up the data. Same thing if it hits my end observation time. It just parks the telescope, shuts the roof, and then I download the data in the morning. So it's really nice. So in the end, I got 13 nights of observation, which is way more than I needed. I was only planning on getting 6, but East Texas thunderstorms happened, so yeah. So I wanted to get at least 2 nights per filter so that I could, again, observe an entire orbital cycle of the star. And in case something happened, I wanted that second night so I could fill in any gaps. And then I got almost 5,000 images. So, yeah. You'll see that I got 2 nights in R, 2 nights in G, and those were both in June, and then a whole bunch of thunderstorms happened. And then I got my I set, but just on the off chance that there were star spots on my star, I wanted to retake my G and R sets, because star spots have a tendency to move. And so I wanted to get all of my sets in as short a time as possible. Hello. So that I could try to pinpoint where those star spots were at a certain time. All right, so then I had to process all 5,000 images. So I mentioned that I wanted to get rid of atmospheric effects. The way you do that is you select comparison stars, and you want these comparison stars to behave the same way as your target star in all three filters. That means you want them to put out similar amounts of light in all three filters. And if you've taken Dr. Ball's astronomy class, you know that what determines the wavelength output of a star is the temperature of a star. So I wanted them to all be similar temperature to my target star, and I wanted them all to be similar brightness to my target star. And then you'll notice this one little guy over here. It's not labeled comparison, it's labeled check. So any kind of measurement or any kind of error correction I did to my target star, I also did to my check star. My check star is not a variable star. It's just constant magnitude. So I know that my photometry is correct if I end up with a graph of my check star's magnitude that is completely level, completely constant. All right, then we use some image processing software. This software, again, is also used with astrophotography. So if you're interested in that, this will help you make composite images. And I compiled those calibration frames I briefly mentioned earlier. So there were 3 types of calibration frames. There were darks, where you leave the camera shutter completely closed and you just take a 0-second exposure. And this accounts for any kind of thermal fluctuations in the chip. Notice, remember we had to cool it? Well, there's still going to be some leftover thermal fluctuations. Biases account for random noise in the chip and also some defects. You can see here you've got these columns that are extra dark. These biases will help us subtract those out of our pictures. And then flats help us get rid of any kind of dust. So you can see these donuts. Those are dust particles that are either on the chip or in the telescope. And then you can also see that this is not an Instagram filter. You've got this vignetting, so it's brighter in the center, dimmer around the edges. And our flats also help us get rid of that because that would also happen to all of our images. Then I had to go through all my images, click through every single one, and take out all the ones that made the frame useless. So extreme cloud cover was one, but those are kind of boring to look at because they just look fuzzy. But this is an interesting one. I have 3 satellites cross through this one picture. So any picture where I had 1 satellite go through it or a cosmic ray hit that was near my comparison star, I needed to throw those out. And then I used Myra to extract the photometry, which was basically just a big Excel spreadsheet full of a list of all the stars, all their coordinates, dates and times, and then brightnesses. Okay, so then if you ever do research, you have to plan for something to go wrong. So up to this point, everything was going way too smoothly. And I tried to get all the data to overlap into a single light curve, and this happened. And as you can see, it's not matching up correctly. You look like you have 2 distinct light curves. I was like, this is not right. So I did some digging, and each image has an observation date on it. And so I looked at the observation date, and I calculated, astronomers, we have a certain calendar that we use to measure time. It's called the Julian calendar. So I calculated the Julian date, and then I calculated this heliocentric Julian date. So when you're on Earth, you know, starlight takes a certain time to reach you, right? But you've got the sun, that's the center of our solar system, that's relatively stationary, and the Earth moves around the sun. And it takes about 8 minutes for light from the sun to get to Earth. So imagine if you were on one side of the sun taking a picture of a star over there. And then 6 months later you decided to take a picture of the same star, but now you're on the other side of the sun. Well, that light is going to take 16 minutes longer to get to you. And that can be an issue. So heliocentric Julian date corrects for that and is the date and time as if you were observing from where the sun is, not from where the Earth is. So we calculated that, We looked at one of the images that was not processed. The heliocentric Julian date matched. We looked at a processed image, it matched. We looked at the spreadsheet, and we did not get a match. In fact, this discrepancy is equivalent of all of my images or all of my photometry being shifted 5 minutes earlier, which does not sound like much, but it was enough to get those light curves not to match up. When you've got a 6.5 hour orbital period, 5 minutes is quite significant. So I reinstalled the software, and then I found out, for some odd reason, this only happens on the student research computer. And if I do this on another computer, this doesn't happen. And that was really weird, and we never did figure out what setting in Myra was causing the issue, but we just went ahead and redid all the photometry on a different computer. And it worked. So in the end result, we get these light curves. So you can see G, R, and I, my filters, they look great, they match up, and here's my check star. Yes, it is a flat curve. So we do have good photometry. And then you can also notice that my star is brightest in I, which is the red and infrared, and dimmest in G. So this indicates a somewhat cool star. It's cooler than the sun. All right. So then I wanted to know exactly how long does it take these two stars to orbit each other. So I used all of my data, and back here. These are overlaps all 13 nights, but I can separate them out into a curve for each night. And when I do that, I can use those curves to find out the date and time of each minima. And I can use this program here. So I did that for my own data. And then I had to go through all the publications ever on this star and all of the times of minima that anybody has ever recorded, and there were 137 of them, including mine. So this screenshot of a spreadsheet doesn't even show all of them. So this column here was all of my observed times of minima, all of my observed times of eclipse, if you will. And then I went through and I used an equation to calculate when all of those times of minima should be based on the currently known period of the star. So I did that, and then that gave me, where is it? This column here, which are my calculated times of minima. Now if I've got my period just right, then my calculated times of minima should exactly match my observed times of minima. But they don't. So what we do is we subtract the two, and we make what's called an O minus C diagram. And you can check and see whether or not the O minus C diagram is linear or quadratic or something else, and each one of those tells you a different thing. All right, so up top you've got my O minus C diagram, and we tried fitting a line to it. A straight line would have just meant that our period was just wrong. We can fix it. It's just off by a little bit. But the linear fit wasn't really the best. We got an R squared value of about 0.29. We want better than that. So a linear fit, not so good. So we tried a quadratic fit. Much better. R squared value of 0.67. And what this means, it doesn't just mean that we could be wrong with our measurement of period. It means that the period is actually changing over time. So it's either increasing or decreasing. Do you see how my parabola is concave upward? Okay, so my period's increasing with time. If it was concave downward, it would be decreasing with time. All right, and from that quadratic fit, we can come up with what's called an ephemeris, which is just an equation that we use to predict times of minima. The important parts are we can get the period corrected to within, I believe that's 10 to the negative 8 Ks. And we can also see that the period is changing by 0.8 seconds every century, so not very much. But if we can find the masses of the star, we can actually use this data to figure out how much mass is being transferred between the stars, which is actually really interesting. All right, so then our computer solution, we had to estimate a whole bunch of parameters, and this is where it gets kind of fuzzy. So if you can use your imaginations for a minute. Imagine that you've got a flat field, right? Okay, and now you have a whole bunch of different holes dug in your field. And one of them is deeper than all the rest, but you have no clue where it is. This is what it was like to try to find my mathematical model. And I'm not sure that I found the deepest hole in the field. But you've got, somewhere upwards of 15 different parameters that you have to adjust to try to find this mathematical model. And when you've got that many parameters, it can be hard to tell which parameter is changing what thing about your model. And it can be really easy to trick yourself into thinking that you found the solution for your star, when really you found one of those shallower holes in your field and not the deepest hole in your field. So we wanted to start by estimating reasonable values for our star. And, well, we use tables to estimate temperatures. We use the appearance of the light curve to estimate orbital inclination. Orbital inclination, if the two stars line up directly with you when you're observing them, that's orbital inclination 90 degrees. If they're off from that, then however much they're off from the horizontal, you just subtract from your 90 degrees. So I thought, based on my light curve, that mine were slightly off from 90 degrees. Mass ratio was also estimated using tables, and the rest of it, these are what are called second order parameters, so we won't really discuss those unless you have questions on them later. So this was my initial rough guess using the software Binary Maker 3. And it was bad. You can see the red line was my observed light curve. The blue line is my calculated one. And they don't match at all. If you want to see it again, though, you can see where the brighter star is eclipsed here and the dimmer star is eclipsed here. Now, it goes kind of fast, so pay attention. But you can kind of get an idea of what the star is doing as that light curve is formed. So we adjusted our parameters. We basically just sat in the program and changed numbers and tried to visually fit the light curve. And we changed some of the numbers, and we found that the orbital inclination was even more off from 90 degrees. The temperatures didn't really change. The mass ratio went up significantly. So it is almost 3. So one star is almost 3 times more massive than the other. And the omega potentials, you can think of those as determining the shape. Since those two are equal, those stars share a same envelope together. They are now in contact. So looking at this estimate, we get a much better fit. Now, it looks good, right? But what's the main issue with this?
That one middle curve.
Yes, that one middle curve. That one maxima is off, right? So if you've got your two stars facing you, okay, then you've got one brightness, you've got one maxima. But if they face you the other way, you would expect the same brightness, right? It's just the other side of the star. But here we've got a different brightness. So the other sides of the star have to be different somehow. They have to be dimmer. Star spots are probably at play here. We've probably got star spots on our other side of our star. So we add spots. And these spots are cold spots. The temperature factor is less than 1. We play around with this. You can barely see, this is not, I have a better model coming up, but you can barely see one of the spots right there. The other one is a little bit harder to see. Much better. Much, much better. So we used our no spot and our with spot sets of parameters, and we put them into Wilson-Diviney, and Wilson-Diviney is an iterative procedure where you just make corrections to all the parameters until you get as good of a fit as possible. And without spots, our orbital inclination still dropped some more. Our temperatures actually stayed relatively the same, which was nice. Our omega potentials are the same, which means we still have a contact binary. And our mass ratio stayed about the same. So we had some pretty good guesses going into it. There's something called third light, which is where you can have light from another object. Not just the two stars, but a third object. Now, for us, we did not find any third light. So that was interesting. And then our residuals are how we measure the fit of the solution. We had about 10 to the negative third. But then we look at our observed light curves and our synthetic light curves, and they don't really match. So you can see the black line is the synthetic light curve from the model, and the circles are my observed light curve, and there's a lot of different places where they don't match. Your maxima don't fit. The computer solution is trying to split the difference in the observed light curve. There's some asymmetry that's not matched. It matches here, but it doesn't match here on this slope, and it doesn't match on this slope. And yeah, it's just all kinds of off. And the depth of the secondary minima is wrong. For that matter, the depth of the primary minima is wrong. So the computer's just got it all wrong at this point. So we add spots. And in this case, our temperature does change a little bit. And we have our spot parameters. Notice that our co-latitude and longitude of our spots have really big errors. You remember what I said earlier about wanting to take data all in the same space of time, just in case the spots were moving? Well, this solution uses all of my data across all those 2 months. So it might make sense that if I do have spots, that those spots did move over the course of those 2 months and introduce some large errors in their locations. Again, no third light, so as far as we know, no evidence for a third body. But the residuals dropped by an order of magnitude, which is excellent. So 10 to the negative fourth, well, 10 to the negative third if we round up, but. All right, and looking at our light curves, they fit a lot better just looking at them. So we do have slight issues. The G curve, it's got a little bit too much light right here, just a little bit off. And our primary minima for the I and the R, just again a little bit off, but that could totally be due to our spots moving over the course of our data taking. Okay, so we plugged this mathematical model into Binary Maker 3. And this is a pretty good model of what my star looks like. So again, just to remind you, I can't distinguish between those two stars in my telescope. It just looks like a single dot of light. But just from the graph of brightness over time, we can get a model of what the star could look like. So, pretty cool. Okay, one last thing I did. I wanted to kind of interpret my results. There are actually 2 types of W-UMA stars. There's a few that don't fit these 2 categories, but most fall into these 2 categories. And these 2 types are distinguished by several features, one of which is their mass ratio. So the mass ratio from my mathematical model fit within the range of a W type. If you notice that my temperatures were about 5,000 Kelvin, well, that is definitely less than 6,000 Kelvin, definitely not greater than 6,000 Kelvin. So again, it falls under the category of a W type. And then if my light curve was stable at the maximum, like an A type is, it would be flat at the maximum. And was it flat? Nope. So it was changing. So I have a W type. The period, we noticed that the period was changing. We had a quadratic fit to our period study. So again, W type. And we can't 100% say what the masses of my 2 stars are. We can say what the mass ratio is, but unless we get something called spectral data or radial velocities of my star, where we can actually tell the sizes of my star. We can't actually nail down the masses. However, there are lots of papers out there that offer reasonable estimates of the masses of my star, and if we use those, we can figure out the mass transfer rate between my two stars. So the smaller one is actually feeding mass to the larger one. And if we use those estimates, we find out that my star is actually transferring mass at the rate of 10 to the negative solar masses per year. Yes, solar masses. It's a large enough amount of mass that we can't use kilograms. Or we can, but it would be a ridiculous number. So, for all intents and purposes, my star is a W-type W-unit star. So to summarize, we've got probable mass transfer happening in my star from the smaller one to the larger one. Something I did not point out, but if you look at the leftovers, if we use that ephemeris that I mentioned earlier, the prediction of my calculated times of minima, we get these leftovers from the observed times of minima. Notice how they're steady, and then they jump, and then they jump down the other way. That could indicate that we do have a third body in the system. We do have some third object way out here that is possibly orbiting in a highly elliptic orbit around my two stars. But since we didn't get any third light, we don't have confirmation of that yet. And my period data only spans about 20 years. So we don't really have enough data. We need at least 10 more years of observation there. It's probably a late type star. It seems to be in the literature to be a K-type star, but we can't get the luminosity class again without spectral data. It's got some kind of magnetohydrodynamic activity. Put that one in your back pocket. Basically, it's got star spots. This is a picture of the sun. There are star spots. And you can see how these star spots are localized in certain regions. So it might be that my star does not have two large spots, but it's got several smaller spots localized in certain areas. And it's a contact W-type W-unit binary. So I wanted to thank Mr. Michaels. He's not here today, but he graciously allowed me to use his observatory and a whole bunch of his Excel spreadsheets and macros. And then these are my references.
That's a lot.
It is a lot. Are there any questions? Yes, Dr. Henry.
So you've got this parameter fit that has over a dozen different parameters.
Yes.
And to me, the one parameter I expected to see but didn't see on your list was the radii of the stars. And it seems like it must be in there somewhere because it shows up in the model when you do the model. Is that not a free parameter? Is it a parameter that comes from something else?
We use a ratio relative sizes, but we don't
Okay.
use the actual radii. The radii themselves, again, have to come from radial velocity measurements. And
Okay.
so
So when you stick in the ratio of the masses, does that contain information about the ratio of the radii too?
yes.
Okay.
So we use something called the Roche model,
Sure.
where we're looking at the equipotential surfaces around the stars.
Okay.
And that constrains the shape of the stars. And then we use that in the model to calculate the light output of each element on the surface of the star. So, yes, Corey.
Yeah, so your star has spots. Does it seem to have more spots than is typical for an eclipsing binary, or is the amount of spotting there pretty typical for that kind of star?
It's pretty typical. We could add more spots to our model, but we don't have the justification for it. So if we were to add 3 or more spots, then people could just say, oh, you're just being,
Right.
you just want to find the best possible fit.
Right, that's why I was wondering how typical it would be for a star like that.
Yeah. So maybe if we had future data, we could add more, but at this moment, 2 is about all we can do. Yes.
Based on the fact that the spots might be unusually large, could there be possibly any stars that have these unusually large sunspots?
Yes, there actually are, and they actually are K-type stars. They have been observed to have these massive star spots. But that's a unique situation, and so it's more likely that we have smaller spots just within a certain region. But again, we don't know. We can't see this star, or at least resolve it. Yes.
So you mentioned binary star and eclipsing binary, are there any non-eclipsing binaries?
Mm-hmm.
So like two stars that are so close together but they don't like rotate at all.
Okay, if
Because
they
that's at least what I assumed from eclipsing.
right, so the eclipsing part actually has more to do with the orbital inclination, which is, I mean, there's so many binary stars out there, it's almost a random parameter. So if you have two stars that are facing you, they can eclipse. If they're slightly tilted, they can partially eclipse. But if they're not tilted enough, they're going to be rotating this way relative to you, so they won't ever pass in front of each other. If they were stationary, they would fall into each other and collapse. So they have to have some kind of rotational motion in order not to collapse into each other. Yes, Dr. Ball?
I assume that the reason the period's changing is not because of gravitational waves being emitted, but rather the mass transfer that's taking place between the two stars. Because that's what the primary reason for the changing period, right?
Correct.
Orbital decay.
Correct, yes. Although that jump that we noticed could also be caused by a third body. So, but yes, the general quadratic trend, that's probably caused by mass transfer. Yes?
So you were mentioning the third body. What types of things are there? Planets or extra stars or?
Could be planets, though planets might not be massive enough to cause that huge change in period. Generally, at least what I understand from my advisor, the third body is a small red dwarf. That's usually in an extremely elliptical orbit. So it could be at this time, it's way away from my two stars. That's why we're not seeing any third light. So maybe if I took data again at a later time, I would see third light because that red dwarf might be closer to my two stars, if that's what it is. Yes?
So you mentioned about the mass transferring and how fast it's going. Is that very dependable on the star, like how fast can two stars merge to each other?
Ooh, that is a good question. So you're asking if the mass transfer affects the rate of merging? I don't remember coming across that in the literature. I do know as they rotate, they do tend to lose energy to gravitational waves as well as other sources. And as they do lose that energy, yes, they will eventually merge. It's just going to be a really long time. Other questions? Yes.
Building off the research you've done, what is further research telling you to do?
So there's something called a Q-search. So I mentioned that flat field with all of the different holes in it. So my mathematical model might have found one of those shallower holes. I tried to get around that by making a reasonable estimate of what the parameter should be. If you're really going to do a good job and try to find the deepest hole in the field, you want to set the mass ratio and choose a whole bunch of different values of the mass ratio and then just crank out a solution for each value. And it takes a long time. But then once you do that, then you can see, oh look, I've got a dip here in the residuals at this particular solution. This is the solution of my system. So that would be one of the things I would do in the future.
Okay, well, if you have more questions, you can join us for lunch in the Joyce Room, Dr. Ball. And let's thank our speaker one more time. Okay, we'll see you all next week.
You said one star and then you said two stars. What is it? Like